Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 4, Lesson 2 on rational exponents. So in our first lesson we reviewed the basic exponent properties, and I hope you actually saw that before you take a look at our rational exponents lesson, because this in theory should be a brand new topic for you in Algebra 2. Some of you may have seen rational exponents back in Algebra 1, which would be cool because then you have like a little bit of a head start. But let's kind of get into it. Now let's review an important exponent property. You should now be comfortable with integer exponents, right? Those are both positive whole numbers and negative whole numbers. In this lesson we will learn about rational, also known as fractional, exponents. To do so we must first review an important exponent property and a common notion about roots and powers. Alright, so let's just take a look at exercise number 1. Recall the product property of exponents and use it to rewrite each of the following as a simplified exponential expression. There is no need to evaluate any final numerical answers. All right, so basically this is just me asking you to review the fact that when we have a quantity, like in this first one, letter A, 2 to the third, then raised to the fourth, we simply multiply the exponents. So let's just do this one together. This should be easy, right? If I have 2 raised to the third, raised to the fourth, the product property of exponents says that that's 2 to the 3 times 4, which is 2 to the 12th. All right? This property, strangely enough, is going to be the basis of the rest of what we really do as we seek to understand what a fractional exponent really is. So pause the video now and go ahead and rewrite each one of these by using that property. All right, simple enough, right? If we have 5 to the minus 2 raised to the fifth, raised to the fifth, that's got to be 5 to the negative 10th, right? Negative 2 times 5 gives us negative 10. If we have 3 to the 7th raised to the 0 power, right? So 3 to the 7th raised to the 0 power, that must be 3 to the 7 times 0, which must be 3 to the 0. Now you might recall from our last lesson that that's also equal to 1, but it said we didn't have to find any numerical values. And finally, if we have 3 to the 2x raised to the fifth, that would have to be 3 to the 2x times 5, and that would be 3 raised to the 10x. All right, now again, the point here is to just simply review that product property. When I have something raised to an exponent, raised to another exponent, I can rewrite that expression as an equivalent expression by multiplying the two exponents together. All right, let's keep going. Exercise number 2. Simplify each of the following expressions based on the inverse nature of powers and roots. All right. Well, let's take a look at letter A together. Here, we have the square root of 25 squared. Now, this one is easy to think about because we all know that the square root of 25 is 5. So, we could easily rewrite this as 5 squared, and of course, 5 squared is 25. Now, it's not a coincidence that we got the number that was originally under the square root symbol. Because if you remember way back to when you originally thought about what this was, right? Your teacher always said, well, that's equal to the number that when you square it gives you 25. So if you think about this, if I said, take the number that when you square it gives you 25 and square that number, you should get 25. So like literally, this expression says take the number that when you square it gives you 25 and square it, you better get 25, because if you don't, then there is totally something that's a disconnect there. And the reason that's important is that this is easy enough to do. But when I take the square root of 117 and I square it, right, I don't know what the square root of 117 is off the top of my head. It certainly isn't an integer. It's not a nice number. But, right, if I take the number, right, that when squared gives me 117 and I square it, well, then what I get is 117. Okay? Square roots and squaring are inverses of each other. They cancel each other out, if you will. Now, let's take a look at letter C. Here we have the cubed root of 8, quantity cubed. Well, similar to letter A, right, it's easy enough to say the cubed root of 8, right, is equal to 2. And 2 cubed is equal to 8. So just like before, right, we really shouldn't need this intermediate step because the cubed root of 8 is the number that when cubed gives you 8. And if I take the number that when cubed gives you 8 and I cube it, I'm going to get 8. And therefore, when I take the cubed root of 37 and I cube it, I'm just going to get 37. Now finally, and the most important piece of all, if I take the nth root of a and I raise it to the nth power, well, then that has to be a, right? Because the nth root of a is the number that when I take it to the a power gives me, or to the nth power gives me a, and then I raise it to the nth power, then I have to get a. And it can seem very abstract, right? Oh, what do I get when I take the cubed root of 37 and I cube it? Well, I've got to get 37, right? And just like when I take the nth root of a and raise it to the nth power, I have to get a. Now, all of that, believe it or not, is preparing us for fractional exponents. And you might be like, I don't see how that's going to prepare us for fractional exponents. But let's now set it up in the next problem. All right, any new type of exponent that we introduce should be consistent with our 3 exponent properties. We will use the product property of exponents to understand fractional exponents beginning with ones of the form 1 over n. So the first thing I want to do is understand something like a fractional exponent of 1/2, or of 1/3, or 1/5, or 1/10. I want to understand that. So let's take a look at exercise number 3. Consider the expression a to the 1/2 squared. Letter A, use the product property of exponents to show that this expression must be equal to a. All right, well, this is easy enough. Let's just do it together, right? The product property of exponents says that if I have something raised to a power raised to another power, I should multiply those two powers, or I can multiply those two powers. In other words, a to the 1/2, no matter what that means, raised to the second, has got to be, not that, but a to the 1/2 times 2. And of course, a to the 1/2 times 2 is a to the first, and that's just equal to a. Now, in letter B, it says, given letter A and exercise number 2E, what can you say that a to the 1/2 is equivalent to? Well, hold on. Let's just go back to a second. 2E says that if I have the nth root of a and I raise it to the nth power, I get a. Now specifically, right, that means that if I have the square root of a squared, I have to get a, right? But I also know that a to the 1/2 squared is equal to a, right? That's just based on the product property of exponents. But that must mean that a to the 1/2 is the same as the square root of a. So what does a fractional exponent mean if there's a 1 in the numerator of the fraction? It means a root. Now, specifically, right, a fractional power of 1/2 means a square root. And you might be like, wow, that's a little bit weird. But again, right, a square root when squared just gets you back to the original kind of quantity. And a 1/2 power when squared also gets you back there. But you don't have to take my word for it. You probably trust your calculator even more. So let's take a look at letter C. Test the equivalency you established in B by evaluating each of the following on your calculator. All right, so here's the key, right? You should already know what the square root of 4 is, and the square root of 9, and the square root of 16, and the square root of 25, right? You should even know where that square root button obviously is on your calculator. But let's take a look at what happens when we raise these numbers to the 1/2 power, right? And I chose these in a very specific way, right? So if I take 4 and I raise it to the 1/2 power, right, I get 2. Which is, of course, the same as the square root of 4. But then again, it's also the same as 4 times 1/2. So that one you might be like, well, I don't know, maybe 4 to the 1/2 just means 4 times 1/2. It doesn't, right? So if I take 9 and I raise it to the 1/2 power, boy, that didn't work. One more time. Oh, really? To the 1/2 power. There we go. I get 3. And as we know, the square root of 9 is 3. What I'd like you to do now is pause the video and go ahead and do the last two. Put 16 to the 1/2 in your calculator, put 25 to the 1/2 in your calculator, and verify that they are in fact the same as the square root of 16 and the square root of 25. All right, well, real quick, let me just do this. This is equal to 2. This is equal to 3. Really fast, let's do it. I've got 16 raised to the, let's see if I can do this now correctly without having anything weird happen. 16 to the 1/2 is 4. 25 to the 1/2 is 5. Now, that is probably the most common fractional exponent that you see out there, a fractional exponent of 1/2, and that's probably because the most common root you have out there is the square root, all right? So a 1/2 power is the same as a square root, which is kind of cool. And whoop, I don't know why I just did that. Let's go into full screen, and let's keep going. Exercise number 4. We can extend exercise number 3 to all fractional powers of the form 1 over n. Fill in the following. Well, this should be no surprise. I know that the cubed root of a cubed is equal to a. Okay? But I also know, based on the product law of exponents, that a to the 1/3 cubed is also a, right? Because 1/3 times 3 is 1, and that's just a to the 1st. And therefore, right, I can say that a to the 1/3 is the same as the cubed root of a. All right, what I'd like you to do is fill in letters B and C. All right, well, the 4th root of a to the 4th is a to the 1/4 to the 4th is a, and therefore a to the 1/4 is equal to the 4th root of a. And of course, we can take this to the absolute extreme. I have the nth root of a raised to the n is a. I have a to the 1 over n raised to the nth power is a, and therefore a to the 1 over n is the nth root of a. So all powers that have the form 1 over a whole number, 1 over 3, 1 over 2, 1 over 10, 1 over 50, right, indicate a root. And the root is specifically that level. So if it's a to the 1/2, it's a square root. A to the 1/3 is a cubed root. A to the 1/4 is a 4th root. A to the 1/5 is a 5th root, etc., etc. All right, and there it is, right? Unit fraction exponent properties. For any whole number n, x to the 1 over n is equal to the nth root of x. Awesome. So, you know, that's nice, but what about fractional powers that aren't of the form 1 over n? Well, let's take a look at them in exercise number 5, and the key is going to be, again, The product property of exponents. Let's take a look at exercise number 5. Let's think about the expression 4 raised to the 3/2. Letter A. Fill in the missing blank and then evaluate this expression. All right, so we're going to run the product property of exponents backwards in 2 different ways. So 4 to the 3/2 can be thought of as what raised to the 1/2? Well, just writing it kind of backwards, we can say that 4 to the 3/2 is equal to 4 to the 3rd raised to the 1/2, right? I mean, by definition, what the number 3/2 is, don't worry about the 4, what the number 3/2 is 3 times 1/2. Well now, right, 4 to the 3rd is 4 times 4, which is 16, times 4, which is 64. And now, based on the work we just did, 64 to the 1/2 is the same as the square root of 64, and that's equal to 8. So 4 to the 3/2 is equal to 8. Now, what did we really do here? Right? We used our knowledge of both sort of just normal exponents, right, 4 to the 3rd, and fractional exponents, something to the 1/2, but we had to break 3/2 up into that whole power exponent and that fractional exponent. But the cool thing is multiplication is commutative. 3/2 can be thought of as 3 times 1/2, but it can also be thought of as 1/2 times 3. So that's letter B. Let's take a look at that. Fill in the missing blank and then evaluate this expression. 4 to the 3/2 equals blank to the 3rd, right? Well, again, because it's a little bit small, let's do this together. 4 to the 3/2 can be thought of as 4 to the 1/2 to the 3rd, right? Because 1/2 times 3 is 3/2. But now that can be thought of as the square root of 4 to the 3rd, right? The square root of 4 is equal to 2. So that's 2 to the 3rd, and that's also equal to 8. So in other words, when you have a fractional exponent like 3/2, and let me write it a bit bigger, we can always think about the denominator as being a root. When the denominator is 2, that's a square root. When the denominator is 3, a cubed root, 4, a fourth root, etc. And then the numerator is what it's always been, just a normal garden variety power. You know, which one do you do first? Do you do the power first, then the root, or the root first and then the power? And the beautiful thing that A and B shows us is that it does not matter. Now, let's just verify this, letter C. Verify both A and B using your calculator. We don't have to do them both. We're going to do them both at the same time, right? And just kind of what we were doing before. Let me actually clear this out for a second. Let's clear out our history. What did I have? I had 4 raised to the 3. Why did that happen? To the 3/2. And remember, we got 8. Okay? So again, fractional exponents are actually kind of easy, right? The denominator represents a root, and the numerator just represents your garden variety power. Now, let's go back, view, full screen. Oh, I'm going to just put a check mark there. Letter D. Evaluate 27 to the 2/3 without your calculator. Show your thinking. Verify with your calculator. All right, so let me just write this a bit bigger. Okay, what I'd like you to do is try to figure that out without your calculator. Pause the video now and see what you can do. All right, now, we can think of this in one of 2 ways. We can either think about it as taking the number 27 and squaring it, and then finding the cubed root, or we can think about it as taking the number 27, finding its cubed root, and then squaring that result. Without a calculator, right, it's going to be much, much easier to first find the cubed root and then square the result than it is to square 27. I don't even know what 27 squared is, and then find the cubed root of it. So I'm going to think about this as the cubed root. Actually, let me write the intermediate step. I'm going to think about this as 27 to the 1/3 squared. All right, 27 to the 1/3 squared, which I can then think of as the cubed root of 27 squared. The cubed root of 27 is equal to 3, right? 3 times 3 times 3 is 27. And 3 squared is 9. Now you may have said to yourself, yes, but I can easily just put 27 to the 2/3 into my calculator, and my teacher always allows me to use my calculator. Well, that's absolutely true, all right, but then that's circumventing every single bit of knowledge that we want you to get from this lesson. And don't get me wrong, you know what I mean? If this was like 10 to the 2/3, I'd have to use my calculator because 10 doesn't have a nice cubed root. It just doesn't, right? It's an irrational number. But we want you to understand that what 27 to the 2/3 is, really, at its essence, is the cubed root of 27 squared, or the cubed root, or 27 squared that you then take the cubed root of. Kind of sounds the same in either way. All right. Let's take a look at one last problem. Now, but first let's summarize. Rational exponent property. For the positive rational number, m divided by n, we define b to the m divided by n to be either the nth root of b to the m, or the nth root of b, then raised to the m power. And as we discussed in the last exercise, it really doesn't matter which one you think of first. So let's take a look at exercise number 6. Evaluate each of the following exponential expressions involving rational exponents without the use of your calculator. Show your work. Then check your final answers with the calculator. All right. Well, the first one, letter A, is 16 raised to the 3/4. I know it's kind of small on your screen. What I'd like you to do right now is try to use the ideas of roots and powers to figure out what 16 to the 3/4 power is. Almost always in numerical situations like this, it makes more sense to evaluate the root first and the power second, the whole number power second, because it just makes the numbers smaller, right? So I'm going to just rewrite this. First, let me write it a little bit bigger so you can see it. I'm going to rewrite this as 16 to the 1/4, then raised to the 3rd. That means I've got the 4th root of 16 cubed. The 4th root of 16 is 2. 2 times 2 times 2 times 2 is 16 to the 3rd, and that is equal to 8. And you can easily check that on your calculator, obviously. I won't bring the calculator back out, all right? Let's take a look at letter B. 25 to the 3/2. All right. Well, why don't you pause the video now and see if you can figure out what 25 to the 3/2 is. All right, well again, let me just write it a little bit bigger. 25 to the 3/2, I'm going to say is the same as 25 to the 1/2 cubed. That's the same as the square root of 25 cubed. That's 5 cubed, and 5 times 5 times 5 is 125. Awesome. Now, in our last, in all of this work, all of the rational exponents that we've dealt with have been positive. So let's take a look at one together that's negative. I've got 8 to the negative 2/3. All right, let me just write this up again so that it's a little bit bigger. Now, there are many different ways that you can think about this, all right? You can think about it as the cubed root of 8 raised to the -2. You can think about it as 8 to the -2 raised to the 1/3. You could also think about it as 1 divided by 8 to the 2/3. There are lots of different ways that you can therefore sort of think about this problem. I think I might break it up first like this. I think I'm going to break it up as 8 to the 1/3 raised to the -2 power. All right? Definitely 1/3 times -2 is the same as -2/3. All right, and I'm going to do that because I can then write this as the cubed root of 8 to the -2. All right? Now the cubed root of 8, that's simple. It's 2. So I now have 2 raised to the -2. And now I can bring this in as 1/2 squared. And that is 1/4. Okay? And you'd get 1/4 regardless of the 3 different ways that we just mentioned that you could look at this. All right, let's summarize. It's really nice, I love it in Algebra 2 when we look at something that truly is new. A lot of what we've done so far in the course has been review from Algebra 1 and a little bit from geometry. But fractional exponents are things that probably are new to you, right? And I mean, isn't this always the case with exponents? At first with exponents, it's just, hey, just learn what it means to square something or cube something or raise it to the 4th power. And then we went ahead and we introduced like 0 exponents and negative exponents to you, which were obviously quite confusing, although negative exponents, at least that kind of made sense with maybe division instead of multiplication. But then fractional exponents? Like, what does it mean to multiply by something to 1/2 times? That doesn't make a lot of sense. And yet, by using that product property of exponents, we can see how fractional exponents can be thought of in terms of roots. And specifically, when we have fractional exponents in the form of 1/2, 1/3, 1/4, 1/5, we can look at those as the square root, cubed root, 4th root, 5th root, respectively. When we have other types of fractional exponents, like 7/2 or 2/3 or 4/5, we can then think of them as a combination of roots, indicated by the denominator of the fraction, and just normal powers, indicated by the numerator of the fraction. We'll be seeing fractional exponents throughout this course, and you'll see them in every math course that you see from now on. So it's a really good idea to sort of kind of really understand what they mean, what they represent, and how to deal with them, not just on your calculator, but also up there in your head. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.